Welcome. My name is Jennifer Cedillo, and I will be your instructor for this section and for yeast propagation. In this lecture, I will discuss yeast storage and handling in the brewery. Before viewing this video, please read Chapter 5 of the Yeast book by Chris White and Jamil, as well as Chapter 10 in the Standards of Brewing book by Charles Bamforth. After you watch this video, please see the other materials in the module, including a pitching calculation worksheet for practice problems and a review sheet to help you study for the exam at the end of the module. If you have questions or comments, feel free to email me during the course and afterwards. Also, I encourage discussion in the discussion board within the classroom, shown here under Module 5, Microbiology Essentials. I have posted an introduction about myself in the Module 5 discussion shown here. I encourage you to post an introduction about yourself if you have not done so already in the classroom. I think the discussion board is a great place to hold conversations in the virtual classroom, so I hope to see you there. Before we begin the lecture, I'd like to go over some basic vocabulary words that I will use regularly throughout the lecture. Pitch can be a verb meaning to inoculating wort with yeast. And so you can say, I'm pitching yeast, I pitched yeast, or any other verb form. It can be a verb. It can also be a noun. And so a pitch of yeast or a pitchable amount of yeast is the amount of yeast needed to reach an accurate pitch rate in wort. Slurry refers to a concentrated form of yeast cells in media, and usually this media is wort and or beer. Pitching rate is the concentration of yeast cells in wort at the start of fermentation. And so, as we'll go through in this lecture, pitching rate is an important concept, and you should be paying particularly close attention to this when you're brewing beer in your brewery. So, what is a pitchable amount of yeast? When we say a pitchable amount, this usually includes the volume and concentration of yeast cells necessary to ferment a specific volume of wort. It can depend on certain factors, including volume, as making 1 barrel of beer versus 15 barrels of beer will obviously require different amounts of yeast. The starting or original gravity of beer will also matter, as you will see that the pitching rate is dependent upon the amount of sugars present in the wort. Also, importantly, the yeast strain used will also affect what is considered a pitchable amount, and we will go through all of these. For simplification in this lecture, we are only discussing pitching rates during primary fermentation. There are certainly different pitching rates that you can use during secondary fermentation and bottle conditioning, and we will not be discussing them in this lecture. The most often quoted pitch rate for ale yeast is 1 million cells per milliliter per degree Plato. This pitch rate refers to when a brewer is reusing yeast and is not a hard fast number. And certainly in your yeast book, Chris White prefers 750,000 cells per milliliter per degree Plato as an optimal pitch rate. Both pitch rates will certainly produce beer, but depending on which one you use, it may alter the flavor components and other characteristics of that beer. For lager yeast, 2 million cells per milliliter per degree Plato is the recommended pitch rate. These are the two major classes of yeast used in most beer. However, there are some exceptions to these rules. A fresh batch of yeast produced by a high-quality lab will need less than this recommended pitch rate because the yeast is in its optimal health state. High-gravity beers will need a higher pitch rate than what is given here. And then if you're brewing with wild yeast or Brettanomyces, the pitch rates will depend on the strain and the characteristics of the flavor that you want in the finished beer. So let's go through an example of a pitching calculation. Before we get started, we need to know that 1 barrel of beer is equal to 31.5 gallons. and 1 gallon is equivalent to 3,785.41 milliliters. So, if you have 15-barrel fermenter, you have 15 barrels of wort in this fermenter, how many milliliters do you have? In order to figure this out, you take 15 barrels, multiply it by how many gallons are in a barrel, which is 31.5, and then multiply that by how many milliliters are in a gallon. So you have 15 times 31.5 times 3,786, we can round. And this will give you 1,788,885 milliliters are present in 15 barrels of wort or beer. So, now that you know how many milliliters are in 15 barrels of beer, how many yeast cells are needed to pitch into this 15 barrels of wort of a 12-degree Plato ale? So, with this word problem, we need to kind of pick it apart and look at the different aspects of it. One of the key words here is ale. Remember that we said ales are 1 million, the pitch rate for ales are 1 million cells per milliliter per degree Plato. If we said lager or we said another type of yeast, then this number may change. So we need a total of 12 million cells per milliliter to get 1 million cells per ml per degree Plato because it's a 12-degree Plato ale. As seen in the previous slide, we know that we have 1,788,885 milliliters in 15 barrels of beer. This is also an important number. So, in order to determine the amount of yeast cells needed, the total yeast cells needed for this beer, to make this beer, we will multiply 12 million cells times the number of milliliters in this given example. So 12 million times 1,788,885 cells are needed. What does that equal? It equals 21 times 10 to the 12th cells total, or this very long number here. So in the worksheet that I provided in the module, I've given you some of these word problems to work on before taking the exam. Feel free to post in the discussion board if you are stuck and need help further with this calculation. And please do review this slide if you are having trouble understanding this concept. So now that we know the number of total cells that we need to pitch, how do we know how many cells we have in order to get the accurate pitch rate? There are two ways to accomplish this. One, the easiest and the most widely used method is that of using methylene blue stain. Methylene blue stain will give you viability of your yeast, and so blue cells will tell you that the yeast is dead, and clear cells will tell you the yeast is alive, so this is important. So you take a yeast sample, you stain it with methylene blue, and then you add a small amount to a hemocytometer, which is shown here. This is the grid of what a hemocytometer will look like under the microscope. The hemocytometer allows for a specific volume to enter the chamber, and therefore you can make a calculation in order to know exactly how many cells are in 1 milliliter of your sample. In order to do this, you must count the cells in the 5 squares as shown here. So you have each corner square and then the middle square. And I'll show you how to count each of these squares in the subsequent slides. An alternative method, which requires a higher cost and equipment beyond a normal microscope and methylene blue stain, is to use propydium iodide. Propydium iodide is a fluorescent stain that will stain dead cells similar to methylene blue. So here's an example. These are all live cells, and this is just under a bright field microscopy. And then you use a fluorescent scope, so you have to have a very specific instrument that allows you to see fluorescence. And here you can see all of the cells that are fluorescing are dead. And so they're equivalent to the ones that are circled here in red. And so in combination, propydium iodide and a fluorescent scope can give you a very accurate viability count. Certainly there are many different ways you can do this. A fluorescent scope, you would still have to physically manually count the cells. There is a product out in the market called the salometer, which is an automated counting instrument, and this uses fluorescence to see live dead cells, as shown here. The salometers allow for very quick analysis of cell counting and should be considered in breweries of a large size. These instruments start out at more than $10,000, so that's something to keep in mind when you're thinking about whether you'll be doing methylene blue staining or propydium iodide. In this example, I'll show you the methylene blue stain in the hemocytometer. And so here you can see methylene blue was used to stain a yeast sample. All of these clear cells are live cells, shown here. And then this cell here that's dark blue, that's dark blue or purple, that's a dead cell. So here what we have is a hemocytometer under a 10x microscope objective lens. And so here we have one of those 5 squares that I told you you'll need to count. So this is just one of them, one field that you will count. And so in order to determine the concentration of yeast in the sample you have, you'll start out by counting the cells in these 4 by 4 squares. And again, there's 5 of them. In addition to counting the cells within this 4 by 4 square, you will also need to count the cells that are found on the top border here and the left-hand side border. You will not count cells in the bottom border, as this one here, or in the right-hand side border. This red square depicts exactly the area that you will count. When you're counting these cells, obviously single cells will count as 1, and you include counting the dead cells, so you're going to count the total cells first. In addition, you have to take into consideration the effect of budding cells. So in this example, we have quite a few cells that are budding, and you can see that the bud in this example is more than 50% of the mother cell. In this case, we would count this as 2 cells instead of 1. If you look at this cell right here, it has a very tiny little bud right there. That bud is less than 50% of the mother cell. Therefore, we would count this as 1 cell. To determine the percent viability, we count the total number of cells, and then we count the total number of live cells. You divide the number of live cells by the number of total cells and multiply that by 100 in order to get a percentage. So in this example, there are a total of 10 cells that you would count in this square. You have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's counting the buds. In this square, you have 1 dead cell, this blue cell here. In order to get the viability, you take the total number of cells, subtract the dead cell, and that gives you the number of live cells. You divide that by the total number of cells and multiply by 100. This will give you 90%. So in this example, this sample is 90% viable. Now you try. Go ahead and pause this video and count the number of cells and determine the viability. Okay, how did you do? If we put the red square around where you should be counting, you can see that there are 13 total cells. This one is right on the border, and this is what I would say is a judgment call, but I'm counting it within this square. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we have a total of 13 cells. We see that there are 2 dead cells, one purple one here and one blue one here. To determine the viability, we take 13, subtract 2, and we have 11. We take 11, divide it by 13, and multiply that by 100 to get 84.6%. How did you do? This calculation, similar to this, will you can find in your pitching calculations worksheet. So I showed you how to count the squares within the hemocytometer, and I showed you how to determine viability. However, you also need to know how to determine to calculate the total number of yeast cells. So in order to do this, you're going to count the number of cells in 5 squares, and you're going to add them all together. You're going to multiply by 50,000 and then multiply by the dilution factor. A dilution factor can be 1, 10, or 100, as I'll show you in a minute. This will equal the number of cells per milliliter that you have in your sample. So, how do you determine the dilution factor? When you have a sample in which you want to count yeast cells, you will most likely need to dilute it. In yeast slurry, you generally dilute 100 times, where in fermenting beer, you'll generally dilute 10 times. When diluting a sample, you can just use regular tap water, as this is not a sterile procedure. You'll use a dilution that will allow you to count between 30 and 300 cells total, so that's total in those 5 squares. If you count less than 30, you've diluted too far. If you count more than 300, you have not diluted enough. For example, if you count only 15 cells in a 1 to 10 dilution, you should use an undiluted sample, which would give you approximately 150 cells total. Generally, dilutions are easiest if we use 1 to 10 or 1 to 100. You certainly can use any dilution you want, but you need to include this into your calculation. So here's an example. You take 1 milliliter of yeast slurry and dilute into 99 milliliters of water. This is a 1 to 100 dilution. You count a total of 190 cells in the 5 squares. What is the concentration of yeast in the yeast slurry that you have? And so the ending will be in million cells per milliliter. The answer is 190 times 50,000. You always multiply by 50,000 times your dilution factor, which in this case is 100. This equals 950 million yeast cells per milliliter. So, do you have to count cells every time you're pitching? The answer is no, you don't have to. There are other ways to determine the amount of yeast you're pitching. However, cell concentrations and viability will definitely improve the accuracy of this. You certainly can pitch yeast by weight alone. The rule of thumb is that 1 pound equals 12.5 million cells per milliliter per barrel of wort, and this is given to you in the Standards of Brewing book in the back, the calculation section. You can also determine yeast pitch, the concentration of your yeast for pitching by volume. In this example here, this is from Yeast Labs. You take a 50 milliliter sample of your slurry You put it into this is a 50 milliliter, and preferably a graduated tube. It doesn't have to be. And then you either subject the sample to centrifugation, or if you don't have a centrifuge, you simply leave it and allow gravity to pull the yeast out of suspension. And so you wait until you can see that there's a clear solution, and then your yeast, packed yeast pellet here at the bottom. So what they're showing here is that if you do this and in your sample only 10% is the packed yeast pellet, then this will be equal to approximately 250 million cells per milliliter. If you go up and you see over 50%, around 55% of the sample is yeast pellet, this is approximately equal to 1,400,000,000 cells per milliliter. So this is something to take into consideration, and certainly something you can use if you do not have a microscope and are unable to count yeast cells. So why is pitching rate so important? Over pitching and under pitching can lead to different outcomes for your beer. A low pitch rate, one that's under pitching, can lead to an increase in off flavors, including diacetyl, which is buttery, excessive esters, which can be fruity or floral, fusel alcohol formation, which can be perceived as alcohol warmth or heat, and then sulfur compounds, which can be like refined oil or rotten eggs, all of these. So all of these flavors can increase if you're under pitching. In addition, your terminal gravity will be higher than what's expected. So that means less alcohol will be produced. Also, you can end in stuck fermentations, which means that the beer no longer ferments out. And then finally, there can be an increased risk of infection. If you do not have a high enough amount of yeast cells, another microorganism can take over and allow for infection.